Okay, the next speaker is Dr. Eran. Hopefully we will see what happens here with his. Trying to get control of the computer, guys. Eva. Yeah, I'd like to be able to control the computer or the mouse, one of those basic things.
You can see the mouse on.
Oh, it's on here, right? So because we slid something over, or what did we do?
Take the cursor to the left.
Take the cursor to the left. Yeah, I see the cursor. Oh, okay, gotcha. I do have it there. Thank you so much. I don't know if you want to attempt this or not, but you're welcome to try. Okay. Okay, so please give your attention to Dr. Maraj, the speaker about hypersonics. Okay, I'm back to the subject of the morning of hypersonic flight, and I'm going to talk about some real gas modeling. Actually, if it works. Oh, that way. Actually, my introduction is brought to explain why it is important, why this subject is important. It was well covered in the talks in the morning, so I'll go very briefly on that. Basically, if you want to transport some payload from one continent to the other, you've got several options. One of them is the airliners, which fly over 9 to 12 kilometer height at about Mach number of 1. And the opposite is ballistic missiles go to space. And there is also the option to use the air breathing street for fast flight, air propelled, and that in the height of 20 to 30 kilometers. Now, when you are talking about hypersonic flight, there is the extreme of very high Mach number, between 15 to 25 Mach number. There is the European project, SIRA, aiming at that direction. In that case, chemical reaction in air play major roles. I'm talking about the association and recombination, but this is not the current scope. I'm looking about more moderate conditions, and these are the mid-range hypersonic flight, Mach number between 5 and 15. There are already several demonstration flight in this field, like a very famous X-43A flew in 2004 for 20 seconds, and it was the best source for a long time for data for evaluation of design tools. There is a very famous case of X-51, flew a bit about 10 years later. It was propelled by hydrocarbon fuel, unlike the hydrogen of the first one. It flew for quite a long time and provided a lot of data. And there are a lot of vehicles now under consideration. Some of them were mentioned in the morning, like the Lockheed Martin SR-72. This is artist impression, so don't base on that. And also Boeing is presenting mock-up of this civilian transport in all the last AA meetings that I've been there, and probably eventually it will fly. What can be said about this, that in this flight regime, there is distinct deviation from ideal gas function. The flow is either calorically imperfect or thermodynamic imperfect. The flow is chemically either frozen flow or in chemical equilibrium. And so there is a minor effect of chemical reactions than the first region that I mentioned. When you consider the selection of which propulsion system to choose for your purposes, you usually look on the ISP, specific impulse, and you can see very clearly that rockets give very low ISP, but constant for all Mach number. For the low Mach number, turbojets and turbofan give the best performance, and here you get both hydrogen and hydrocarbon. But as Mach number grows, their attractivity is reduced, and Raman scramjets pop up. And in the range of between 6 and 15, scramjet is the best option from the point of view of ISP. So if we look at a scramjet propulsion, what is it actually? Again, in the morning, you've seen this picture. It is based on the concept of compressing the flow through a set of shock waves without moving parts. Looks simple, but it's far from being simple. However, a crucial parameter in the performance of such engine is how effective is this compressing effect. And we measure the losses during this compression by the pressure recovery, the ratio of the P total in the entrance of the combustion chamber versus the P total of the free flight. And this is an important metric to evaluate the propulsion efficiency. But there is a question, how do we compute the total pressure in this velocity regime? And let's first find out what actually we want to know. P total, which is the pressure attained and the flow is brought isentropically to rest. It is an important metric of the mechanical energy of the flow. T total is the temperature measured by bringing the flow adiabatically to rest, and it is an important metric for the thermal energy of the flow. And another thing, whatever we measure in supersonic flow, shockwave develops in front of the probe. So shockwave relation or accurate shockwave relation are important features to gain our purposes. In combustion, for propulsion, P total and T total characterize the propulsion potential, certainly together with the fuel energy and the combustion efficiency. We are able to simulate hypersonic flow. Many have shown that this is a picture of measurement and simulation of hypersonic inlet measured by DLR GK01. And you can see here both Schlieren picture from experiment and result from simulation from some Chinese people mentioned below, and also a small effort by myself. And it's not so difficult to reproduce the flow structure, or moderate difficult. However, again, I repeat the question, how do we evaluate the total pressure? And now this question was raised by a kind of a semi-poll by someone at Rafael. He claimed that he talked to 10 graduates of aeronautical engineering, and 9 out of 10 of them were not aware about real gas effects. They were totally in the paradigm of ideal gas and were not aware that might be some difference. It took me by surprise. So I said, I'm not going to leave Stephen to be the only one who's doing the new hype. I'm going to take another hype. And I asked ChatGPT. And so I asked ChatGPT how to compute total pressure for hypersonic velocity, taking real gas effect in account. The answer that I received, surprisingly, is the isentropic relation, which is ideal gas, totally ideal gas. And well, it is ChatGPT, so I argue with that. So I said, but at hypersonic velocity, the flow is calorically imperfect. So the ChatGPT say you are correct. And actually, you might need to want other kind of equation, like van der Waals equation. So basically, ChatGPT is like an aeronautical engineer, typical aeronautical engineer graduate, but has some potential if you probe it. So again, let's look at some of the basics. A perfect gas assumption, it means that we neglect the volume of the gas molecule and the forces between the molecules. Consequently, enthalpy is a function of temperature only. Delta H is Cp times delta T. And the gas constant is the difference between the specific heats. And gamma, which is the relation between the specific heats, is constant. Additional to that, you are well familiar with the isentropic flow relation. Also, ChatGPT knows about that. If we take into account intermolecular forces, we get the van der Waals equation. And in the van der Waals equation, there is N is the number of molecules, V is volume, and B are constants, which are dependent on the gas. And if we look on the P total, by this formulation, we've got additional term to the standard P total. There are also additional equations like Clausius equation and more. However, these equations are approximations. They are not accurate very much at high pressure or at low temperature. And the constant A and B need to be adjusted by experimental data. So I don't have a total accurate solution. Let's see what, if we are talking about approximation, what are the common approximation at our hand? A very pretty old common approximation is the polynomial model. I have introduced it in SUMB 25 years ago, I think. It appears in many CFD software where the specific heat is a function of a polynomial on the temperature in two domains. And it is based on NACA polynomials, which were published, I think, in the 50s or 60s of the previous century. And if we take a typical wind tunnel model HB2, the blunt model, at Mach number in the region we are talking about and moderate enthalpy, you can see that with perfect gas simulation, you get very high temperature stagnation region. But if you use this polynomial model, the temperature in the stagnation region is significantly lower because the effects of the imperfect gas. We went further, and by 2017, myself and Shlomi Shitrit published work about equivalent gas model, where we took about a bit more complicated approach to calculate the specific heat based on both temperature and pressure. This formulation was suggested earlier by Gupta in 1991. The concept here was that enthalpy is calculated for non-uniform SCP, which means that we compute directly the integral of the enthalpy, and then T total is calculated using an iterative process, demanding the following equation to be fulfilled, and then requiring isentropic flow. You can get a formulation for P total using the previously obtained T total. So this model was also applied for the same case of Mach 7 moderate enthalpy HB2 configuration. And you can see here, you can see here that compared with the polynomial model, here the temperature is even lower. So this model is working. And so because we are working since 2018 on combustion with chemical models in much more detailed chemical approximation, I thought maybe I'll check those approximation and see how good they are. So what we are doing right now. Currently, we are using a Cantera, which is an open source software for chemical kinetics. And the Cantera is using various chemical mechanisms which can be pretty detailed, like the Aramco code, or very high detail, like UC San Diego chemical mechanism and other. And out of them, you can make all the chemical calculation much more accurately than the approximated method, which I mentioned before. So the script that I'm showing here was prepared together with Ido Hoffman, who is sitting here. We were looking at dry air, which is typical to the level of light of a hypersonic flow. That is, the air is composed of oxygen and nitrogen. And enthalpy total enthalpy are calculated by their definition. Then you define an algebraic equation for the enthalpy, and you ask it to come to zero. You solve it algebraically. And also, as before, we claim that delta S should be zero, then we can get P total, or alternatively, we can solve a different equation, H of P minus H total should be zero to solve directly for P totals using Cantera. So this gives us both P total and P total more accurately, and also the coefficient. And let's see how well are the approximation working. First, let's look at the original formulation, which I mentioned before, the polynomial model. And here I look at the specific heat here versus temperature for large N of temperature. And I compare the blue line, which is the original polynomial, with the red line, which is the Cantera result, which I consider as accurate. And you can see that the difference between them is less than 1%, which is pretty accurate. But if we go further and make a very small modification in one coefficient in the two region A0, actually I get the green line, which is nearly on the Cantera result, and the difference is now below 0.2%. So to start with, at a moderate high Mach number, this polynomial approximation, as old as it is pretty good approximation. But let's go further. Let's talk about measurement in supersonic flow. I mentioned it in the beginning. So let's add this issue. When you put a probe in supersonic flow, you get a shock wave standing in front of it. And along the shock wave, there is a significant rise in the pressure and losses of P total. And actually what you measure in the probe is after the losses, so beyond the shock wave. For the definition, this one? Yeah, okay. I remind you again, the ideal gas formulation are supposed to give us a lot of data about this type of flow, but they are not enough. And to keep changing the function of the, yeah. Yeah.
The chat GPT.
Yeah, things like that. Yeah, okay. For the definition of indices, here's another plot of the probe. We've got the shock wave in the front. The shock wave I call is 0.1, beyond the shock wave 0.2, and using assumption of ideal gas, there is or there is not. Page down, page down here. Okay, there is the very famous pitot-tube relation, which is very common, but as I said, it depends on ideal gas assumption. Is it good? Well, it's up here. The issue is all this valid for imperfect gas? So let's look. So I said, okay, what are, I mean, I'm not the first person looking at about this issue. What are the common correlation? What are people using to do measurements? So I made my own poll in Rafael and in the Technion. And after asking several people, I was directed to a publication by JAXA, Japanese space agency, about doing measurements in hypersonic wind tunnels. And actually they published approximate relation between real and perfect gas, both for P total, for T total, and for shockwave across the probe for the Rayleigh Pitot correction. Everything that I wanted was just written here. So I said, great, I found the result. But let's read the paper and see on what measurements or whatever they depend. So I read their data. And I found actually they got a reference for an earlier paper from a wind tunnel in Europe. That is 1981. And in this paper in Europe, they got not only this formulation, exactly, it was totally copying and paste from one paper to the other. But what is the source of the data in this European work? I mean, Europe is a serious place and a serious wind tunnel. So I looked again, what is the source of their correlations? And well, okay, now you can see it. These are NACA reports from the middle of the 20th century. They are the source. At least they have done their own work, and they have solved some approximate equations, which currently are not so much in use these days. So I didn't try to solve this equation again, but I said, okay, I got Cantera, I got chemical mechanism, let's check what is correct and what is not correct. So the first thing is P total. P total computed versus a Mach number. And you can see, and here is ideal gas, in blue. There is the result of Cantera, which I consider as accurate, and the JAXA approximation. You can see that as long as you are below Mach 5, all relations are pretty accurate or match each other clear. In the region between Mach 5 to 7.5, ideal gas give under approximation of the P total, which can be pretty large. While the JAXA correlation are pretty good, but once we go beyond Mach 7.5, then it starts to deviate from the Cantera result and give some error. So in a way, this gives you where and how to compute P total. What about T total? It started working again. In T total, the picture is the distribution of T total with Mach is a bit different, but the picture is pretty similar. T Mach 4 ideal gas is good enough, but then there is deviation, and the JAXA approximation are pretty good till Mach 8, but beyond that there is a distinct deviation. All these calculations, by the way, I didn't mention, were done at the flight of 30 kilometers. We can show them the other point. Then I said, what about the pitot tube? When you take it pitot tube, you wanted to make it as small as possible in order to be in the frozen limit. If it's too small, then you've got viscous effect. If it's too large, then kinetic effect until you reach chemical reaction. The typical probe used in Purdue is 0.8 millimeter, and people were calculating flow over such a probe. So I said, why I won't try my hand on that one. And just another comment, there is ARC wind tunnel here in the Technion. I asked them what they are doing, and they said they are using, they are limited to Mach 4, so they're using ideal gas with modified gamma, and this is sufficiently accurate. For these calculations, I used the FU2. It's the NEMO version. It takes real gas and compared with ideal gas, and the real gas is based on mutation plus open source chemical mechanism provided by von Karman Institute. When I've done this computation, you can see on the left temperature, on the right pressure, above real gas, below ideal gas, you can hardly see any difference. So let's look on the distribution along the axis. The first case, Mach 4, a low Mach number, you can see several things. First, there is small difference between ideal gas and real gas. Ideal gas, which is here in blue, match Rayleigh-Pitot green relation, which is not surprising. And the real gas matched the JAXA relation for shockwave. So pretty good. Behind the shockwave, at first, shockwave standoff is the same for ideal gas and real gas, and there are some minor differences. I will discuss them later. Now let's increase Mach number to 8. Now,
Yes.
yeah, I'm a few more slides. Well, here I've added another simulation by Charles, which is LES. Not so much because I wanted the LES capabilities here, which are irrelevant, but because this is a different chemical model with Cantera. And so what you can see when in this comparison, too much. There is a problem of reaction time here. What you can see that again, ideal gas and real gas, the two groups, the two concepts are grouped together. The stand of the shockwave between ideal gas and real gas is different. And also there is a difference between the software, but generally one can see what one expects. And I'll talk about beyond shockwave later. But now let's go to higher Mach number, and that's Mach number 8. And here you can see that the Cantera is now giving you an overshoot of the P total as expected from before. The grouping of the ideal gas and real gas is typical. The difference between the Mach standoff, Mach number shockwave standoff is higher here. And now let's look what happens beyond the shockwave. And here we see an interesting difference.
Just need to wrap it up a little bit because we have to zoom.
Yeah, that's the end, one before the end. What you can see, first, if I take ideal gas, or I take Rayleigh-Pitot relation with gamma 1.4, I get the blue line, which is totally ideal, totally identical. If I take the Rayleigh-Pitot relation with smaller gamma, then I get the green line, which is pretty good agreement with the Cantera result. However, the JAXA relation give me a total under prediction of the Pitot, and because the measurement of Pitot pressure is used for P total, then this under prediction gives a very strong error, when we try to approximate P total at the far field by these measurements. So there is a big question about the JAXA relations in the relation of measurements. So my concluding remarks that in a Personic regime, the credibility of ideal gas approximation are losing ground. Total condition and temperature are significantly affected by real gas effect, and they are very important for propulsion potential. Measurements through shock waves deviate from ideal gas, but the common Rayleigh-Pitot relation provide a better approximation than more exact correlation. The next step should have been measurement in supersonic probe flow in high velocity and high enthalpy flow. It is pretty simple measurement, but accessibility to suitable wind tunnel is not that simple.
Thank you very much.